Section 4.5 dives a little bit further into specifically solving exponential equations. Last class we learned how to do this mostly with no context, although some of you got to the questions on the whiteboards where it had like context, right? The problems where we were solving real world scenarios. But exponential functions appear a lot in a lot of things that we measure or study in science. So we're going to take some time to look directly at exponential growth and decay. Now, exponential growth and decay, I know that you know that the shape of growth goes up and the shape of decay goes down. Awesome. There are more specifics to the equation that we're going to use to represent exponential growth and decay. The formula I want you to highlight right now, the color scheme doesn't really matter today, but we're going to highlight the A equal to A sub 0 times e to the kt power. This formula, which is exponential growth or decay, because the t, which is the input of the function, is up in the exponent, is how we will model a lot of real life scenarios of growth and decay. If we break apart what each thing means, the big A, kind of like the compound interest questions, the big A is the amount of that substance at the end when we're measuring. So if that's population, this is the amount of people that live in a particular place. The A sub 0 is your initial amount. So if it says in year whatever, there were 50 people living in the city, that's your initial amount because it's telling you where we're starting. The E is always an E. It's our base. I want you to highlight the K. I know you're highlighting on a highlight, but I want you to highlight this K. K is very important for us here because K represents the exponential growth rate. K is a constant that represents our growth rate. So we're going to have to spend some time today making sure we can identify the growth or decay rate of a particular function. This is going to be different than the growth and decay you maybe did in Algebra 1 or Algebra 2, where you just looked at the base, and if the base was big, it was growth, and if the base is small, it's decay. This is different. For this type of growth and decay, if k is bigger than 0, so if you have a positive exponent, that's when we're going to be growing. And if we have a negative exponent, k less than 0, that's when we're going to have a decay function. And that makes sense because if we think about our exponent rules, anything to a negative power is the reciprocal, so then it's 1 over e, which is now a small number. But we're going to be looking at specifically this formula over and over today. A equal to A sub 0 times e to the kt. A is the final amount, A sub 0 is the initial amount, k is the growth rate or decay rate, t is time. E always stays the same. So we'll look at a number 1, and you can laugh at my typo here. There was a graph last year, or a table last year when I did this problem, but it wasn't necessary, so I got rid of it, but I forgot to reword the actual question. So ignore the part that says the figure on the right. There's no figure on the right. All we need out of this is to start reading here. It says, in 1970, the U.S. population was 203.3 million, and by 2020, it had grown to 331.0 million. Our first job today is to find or write an exponential growth function that models the data for the years 1970 to 2020. We are trying to fill in A equal to A sub 0 times e to the kt power. The two things you need are an A sub 0 and a k. We need to know the initial amount when we started the study, and we need to know the growth rate. And then we will be able to plug those in, boom, boom, boom. One of those two things we were given in the problem specifically says in 1970, when we're starting this study, the initial population of the United States when we started studying is 203.3 million. So we know that A sub 0 is 203.3 million. What we don't know is we weren't given the growth rate. So we're actually going to have to find the growth rate to be able to write the equation. But no big deal, because to be able to solve for the growth rate, we just need one more input-output pair to be able to solve. And they've given us another input-output pair because we know at time equal to 2020, which is how many years after 1970? 50 years. So at time equal to 50, our output or our population was 331 million. So we have a time and we have an amount that we can plug in. If we have a big A, if we have an A sub 0, and we have a t, the only variable left is k. And we're going to be able to use the skills we learned last class to solve for k. So here's what it might look like. We start by plugging in what we know, which is 331.0 equal to 203.3 times e to the k, I don't know k, so we'll put k right there, times t, which is 50. Again, e is a number, so once I plugged all of this in, the only variable I have left is k. If this was an example given to us last class, what would we do to start solving for k? We need this by itself, because it's the base with the power. How do I get rid of this? Divide. So this is 331.0 over 203.3. Don't actually divide it, just leave it as a fraction. Let me go answer the phone. Okay, sorry. So we have 331.0 over 203.3. This is going to be equal to e to the 50k. Now last class, once the base with the power was isolated, what did we do on both sides so that we could get the exponent? We take the natural log of both sides. So we're going to do the natural log of 331.0 over 203.3 equal to the natural log of e to the 50k. Is anybody's spidey senses going off about natural log of e to the 50k? Natural log and e cancels because that's a log base e of e. That's a property of logarithms. So then I only have 50k left, all right? So this is natural log of 331.0 over 203.3 equal to 50k. I'm still solving for k. So how do you get the k by itself? Divide by 50. So we end up with, in terms of logarithms, natural log of 331.0 over 203.3, all divided by 50. The reason I didn't want you to do the division early of the 331 divided by 203.3 is because you'd round that number, and then we'd be using a rounded number to find another rounded number. We're going to use a fraction, or basically don't type anything in a calculator until it's ready to solve for your variable. But now we can turn to our calculator. What is the natural log of, you see it written on the, I don't want to say it again. So go ahead and type that in. I would recommend using the fancy fraction, perhaps using it twice, if that's your jam. Yeah, so there's going to be a significant number of digits, not like sig figures, I just said that, but like there's going to be a lot of decimals in today's lesson. For me, I like to round to 4 decimals, so that's 0097. When you do this homework in the textbook, it will tell you how to round each question, so just pay attention to that, so you use the correct rounding. Okay, now that we have k, in this problem, we have both a sub 0 and we have k. All we need to do is put them together to write our formula. That means our formula for exponential growth of this population is going to be the growth, or the population is equal to a sub 0, which is 203.3, times e to the 0.0097 t power. That's the formula that represents the population growth of the U.S. from 1970 to 2020. Now, because this exponent is positive, and because it's measuring population, we know that this graph is going to show growth. If we go on to the next question, which then says, by which year will the U.S. population reach 400 million? We're going to use that formula we just wrote to solve this question. If it says by which year, what variable are we looking for? T. So let's fill in everything we know, leaving t as the variable. We know we want the amount to reach 400 million when the initial amount was 203.3 times e to the k, which is 0.0097 times t. Now these steps are going to start feeling very familiar because we still want to solve for t, and t is still stuck up there in the exponent. So we basically repeat the steps. We are going to divide by the initial value, 203.3. We are going to take the natural logarithms of both sides. we are going to cancel out the natural logarithm of e using that property. We are going to solve for t by dividing by the coefficient, which happens to be our growth rate. You see how those were the same steps? Yeah, a few different numbers. But essentially the same steps. This time we're solving for t. When we throw that into our calculator, what do we get as the number of years since 1970? Did you get, I know y'all are still typing because I can hear it, 0.771. Now if you answered with this, that technically would be counted wrong because of the way that the question was phrased. It did not ask how many years has it been. It asks specifically, by which year will the U.S. population reach 400 million? So what should we do with this number we got for t? Not plug it in. Not to 2020, but to 1970. 1970 is year 0. So this is telling me it has been 69.77 years since 1970, which means what year will this actually happen? It'll be the year 2039. So just be careful when you're reading these questions. If it asks you how many years, you're returning t. If it asks you in what year, make sure you provide it a contextual answer of the year 2023. So there's a process that paleontologists, I guess, amongst other scientists have developed called carbon dating, where they can look at like really old stuff, like fossils or things from ancient societies, and they can figure out how old it is. And they look at the amount of carbon that's remaining in that object, because carbon decays over time. That's what all of this the little exclamation point box is explaining carbon dating. But specifically, a lot of elements that are very common in the world, we've discovered what is called their half-life. And a half-life is the amount of time it takes for a substance to decay by half. For carbon-14, the half-life, or what it takes to become 50% of what it started as, takes 5,715 years. It's called its half-life. And what scientists have done is they've used this fact, knowing this decay rate, this half-life, we've been able to create a decay function for carbon-14, which then allows us to carbon date really old stuff and figure out how old it is. So let's take the fact that after 5,715 years, a given amount of carbon-14 will have decayed to half of the original amount to find our exponential decay model for carbon-14. So here's what we know. We know that if we are writing a model, we need an a sub 0 and we need k. For this problem, we're actually going to let a sub 0 be a sub 0. But we know that at a sub 0, the amount of the carbon-14 in the object is 100%. It has all of its carbon-14. As we keep going and we keep going, we eventually will lose carbon-14 as we go because it's decaying. What we don't know is we don't know at what rate it is decaying. However, we have a second input and output pair of values here. It says that after, so time, 5,715 years, the amount of carbon-14 that would be left in something is half, or 50%. So we can use the fact, even though we don't have an actual measured amount for this example, we know how the original amount, 100% carbon-14, and the half-life, 50% of carbon-14, we can use those as the input and outputs for our examples. So what we would do is for the formula A equal to a sub 0 e to the kt, we would put 50%, but we'll use it as a decimal, 0.5, is equal to 100%, or 1, times e to the kt power. But we don't know k, we do know t. So again, even though we don't have an actual amount of carbon-14, not like 12 grams or something like that, we know it had all of the carbon-14 at the beginning, and it loses half of it by 5,715 years. Just like we did on the other page, we need to solve for k. What should I do first to isolate the base? Divide. What are we dividing by? 1. Doesn't really do anything, so, okay. We have 0.5 equal to e to the 5715k. What do I do on both sides? Natural log on both sides, so natural log of 0.5 equal to the natural log of e to the 5715k. Those cancel. We see how these steps are repeating. We would get the natural log of 0.5 equal to 5715k. And if we're solving for that growth rate, in this case decay rate, we divide by 5715 on both sides. This is going to be a very small number, and I need everybody to type it in a calculator because I want to alert you to what your calculator is telling you when it spits this number out at you. So grab your calculator, type it in. Your calculator is probably telling you that k is approximately equal to 1.2129 and then e minus 4. Do y'all see that? What does the e to the minus 4 mean? Yes, it's our scientific notation, times 10 to the negative 4 power, which means we're going to move that decimal point 4 times to the left, meaning our actual k value we want to use is negative 0.00012. I think we're stopping there. 121. We're going to round to this decimal. Again, our textbook would tell us, make sure you round to the bleep, bleep, bleep decimal. And we do that. 6 decimal places in this example. That means that we can write an equation for the half-life of using the half-life of carbon-14 to talk about the decay of carbon-14. That formula would be the amount of carbon-14 left is equal to the amount that we started with times e to the negative 0.000121 times t. Now, a follow-up question you might have is, why didn't we use a number for a sub 0? We weren't actually given a number yet. We just know that it starts with all of its carbon-14. If we were told it has 12 grams to start with, we would put 12 right there. But this is not for a particular element. This is just carbon-14 in general. So let's see what it looks like to do this for a particular object. Have y'all ever heard of the Dead Sea Scrolls? Do y'all know what that is? So in 1947, these earthenware jars, which is like clay jars, dirt jars, right? Containing what are known as the Dead Sea Scrolls, which are copies of the Old Testament, were found by an Arab Bedouin herdsman in like the hills. This is like true. This actually happened. Scientists studied them, and they indicated that the scroll wrappings contained 76% of their original carbon-14. So scientists used this fact to be able to estimate the age of the Dead Sea Scrolls. So how old were these things we found from this ancient civilization, right? They buried the thing, we found it. We're like, hey, how old is this tool? How old is this thing that we found? How old is this dinosaur bone when we find it? This is what we're doing. So what we're going to do is we're going to take what we know, which we know now, the amount found when we dug them up was 76%. And since we're talking about a percentage of its original carbon-14, that means we're still going to use a sub 0 being 100% of its carbon-14. So if we fill in our formula with this amount left over and this initial value, we have everything we need to solve for the time. We would have 0.76 equal to 1.00 times e to the negative 0.000121 times t. Make sure you don't accidentally move that decimal place. There's 3 zeros and then 121. We would divide by 1 on both sides, which doesn't do anything. We would take the natural log of both sides. Cancel out the natural log and e, log base e of e. We get natural log of 0.76 equal to negative 0.000121t, which means we can solve for t by dividing natural log of 0.76 by negative 0.000121. Same steps we've solved this entire time, yes? We throw this in our calculator, making sure we give it the correct number of decimals, 0.000121. Which we should get 2,268.073. I guess I didn't write down a fourth decimal. What's the fourth decimal? 1? Thank you. Which means in 1947, when these jars were found, they carbon dated them and found that the scrolls were 2,268 years old. As a little bonus question, how old would these jars be today? How old would the scrolls be today? (2,346 years old today in 2025. Which is pretty cool. Because this is how we know how old dinosaurs are when we find their fossils. And that's cool. Questions, comments, concerns. We've now seen this process of solving for one of the exponents in 4 different examples. I know it's been 2 examples, but we've done it 4 times. Are we feeling okay with that process? Fabulous. Now, when we start talking about population growth, like that first example when we were talking about the US population, theoretically, if we were writing an exponential function, that exponential function has no upper bound, which means eventually we would be trying to conjecture that the population of the United States would reach infinity. Does that make sense? No, because in real life, there are going to be what are called limiting factors to the amount that something can grow. Because if you're measuring something about population, the number you're using can't get bigger than the population. In which case, we now need to look at what are called logistic growth models. Not exponential, not logarithmic, logistic. Do you see the difference in how that's spelled? A logistic growth model is a growth model that takes into account the fact that in real life, things can't go off to infinity. They're eventually going to plateau out at a particular number. The formula for logistic growth is right here. And it's crazy looking. I'm not going to make you do much with this function except be able to speak to it, so use it a little bit and talk about its constraints, which is really pretty simple. If you look, there's a letter C on top. That letter C is called the limiting factor or limiting size of that expression, of that equation. That is the horizontal asymptote that actually exists on the top of the graph that's bounding it from going off to infinity. My friends who take AP Pre-Cal or Cal, if you'll notice this part, which is concave up, that's your normal exponential function. But this section, we wouldn't call this concave up anymore. This would be considered concave down, which means the rate at which we are growing is getting smaller and smaller because we're plateauing out at that limiting size. Now this looks crazy, but C is going to be a number that the equation gives you, the limiting size. A is going to be a number that the equation gives you. E is a base, B is your growth or decay factor, T is your time. So for the most part, the only thing we're going to be filling into these formulas is the time, because the rest of it is found very complicatedly. That would be a whole other thing. We're just going to work with the actual function, make sure we understand how it works. So for example, the figure on the right shows the number of new coronavirus cases in the United States for 7 selected days in 2020. The function f of t equal to, you can read that, models the number of new coronavirus cases in the United States t days after March 14th, 2020. That was the day of the shutdown. So this is measuring new COVID cases as they came available. This has a limiting size because there's not an infinite number of people that live in the United States, correct? There is a cap for the number of people who could get this disease. So this, while it is growing exponentially, does have a limiting size on it. So that makes it a logistic growth as opposed to just straight up exponential. The first question here says, use the model. This is the model. Let's highlight it so we can find it quickly. F of t equal to 26,462 over 1 plus 62e to the negative 0.53t. Use that model to determine the number of new coronavirus cases on March 14th, 2020. Okay, if t is measured as the number of days after March 14th, 2020, how many days after March 14th is March 14th? Oh, it's the same year. So how many years after March 14th is March 14th? 0 days after. That means we're finding the initial value here. We're finding the value on March 14th. So what we're going to do is we're going to take this function, f of 0. That means that all we're going to do is in our calculator, evaluate what this function would give me if I plugged in 0 for t. Now, I said this in my last class and not everybody trusted me. You must use either the appropriate parentheses to make sure you're actually dividing by the entire denominator or just use the fancy fraction in the calculator. But we're going to take a pause and we're going to figure out the number of people who had, the number of new COVID cases on March 14th, 2020 based on this model. Okay, we should get that this is approximately equal to 420.0317. Is that what you guys got? Now this question wants us to also estimate between these 420 cases, because we're just going to round that to something that makes sense. How does this compare to the actual information seen in the chart? So if we look at the March 14th in the chart, did our model over or underestimate? Overestimated by how many? By 6. That's not bad. Okay, what if we chose another day to check our model? It says use the model to determine the number of new COVID cases on March 24th, 2020. What number am I plugging in this time? 10, because the number of days after March 14th would be 10. So we're doing t equal to 10, which means f of 10. So in my calculator, I'm going to have 26,462 over 1 plus 62e to the negative 0.53 times 10, which since you already have this calculated from last time, just go up, copy paste it. So you know how to do that part, right? Scroll up and highlight what you typed in, press enter, it will retype it for you. And then you can just go change the 0 to a 10. We should get 20,208.039, which of course will round to the nearest whole number integer because it's cases of COVID. So 20,208 cases. If we compare that to the actual data on March 24th, did our model over or underestimate? This time it underestimated by 133. A little bit more off that time. So here's another question that comes from the equation itself. It says, according to the model, what is the limiting size of f of t, the number of new COVID cases in the United States per particular day? Limiting size. Where did we find that in the equation, the limiting size? Yeah, it's just c, which means it's just the number from the numerator. So what is the limiting size of this function? That's it. The limiting size is 20... Hello, I would like to write that in orange, please. Is 26,462 cases. So your logistic growth puts a little bit of a reality check, air quotes, on an exponential growth function because really a lot of these things are not going to grow to infinity. There's going to be some sort of stopping point for them.